In today's fast-paced world, the realms of semiconductors, electromagnetism, superconductivity, and mechanical engineering play a pivotal role in shaping our daily lives. These interconnected fields form the backbone of modern technology, driving innovations that power everything from smartphones to advanced medical devices. Semiconductors are essential for creating microchips, which are the brains behind our electronic devices. Meanwhile, electromagnetism governs how these devices communicate and function, while superconductivity opens doors to energy-efficient technologies. Understanding the behavior of atoms at a microscopic level is crucial for engineers and scientists as they design circuits that enhance performance and efficiency. This video will take you on a journey through these fascinating concepts, revealing how they intertwine to create the technology we often take for granted. Get ready to explore the intricate dance of science and engineering that makes our modern conveniences possible, and discover how these innovations impact your everyday life in ways you might not have realized. Semiconductors are the unsung heroes of modern electronics, bridging the gap between conductors and insulators. Conductors, like copper, allow electricity to flow freely, while insulators, such as rubber, prevent it. Semiconductors, on the other hand, have unique properties that enable them to conduct electricity under certain conditions, making them essential for controlling electrical currents. One of the most significant applications of semiconductors is in transistors and diodes. Transistors act as switches or amplifiers in circuits, while diodes allow current to flow in one direction, protecting sensitive components. These devices are foundational to everything from computers to smartphones. Key materials used in semiconductor technology include silicon, which is abundant and cost-effective, and gallium arsenide, known for its superior efficiency in high-frequency applications. By understanding the role of semiconductors and their unique properties, we can appreciate how they power our devices and drive technological advancements in our everyday lives. Electromagnetism is a fundamental force that describes the relationship between electricity and magnetism, two phenomena that are intrinsically linked. When an electric current flows through a conductor, it generates a magnetic field around it, and conversely, a changing magnetic field can induce an electric current. This interplay is the foundation of many modern technologies. One of the key principles in electromagnetism is Faraday's law of induction, which states that a changing magnetic field within a closed loop induces an electromotive force, EMF. This principle is crucial for the operation of various electrical devices, as it allows for the conversion of mechanical energy into electrical energy and vice versa. Everyday examples of electromagnetism include electric motors, which convert electrical energy into mechanical motion, and generators, which do the opposite by converting mechanical energy into electricity. Understanding these principles not only highlights the significance of electromagnetism in technology, but also reveals its impact on our daily lives. Superconductivity is a remarkable phenomenon where certain materials exhibit zero electrical resistance and expel magnetic fields when cooled below a specific temperature, known as the critical temperature. This unique property allows superconductors to conduct electricity without any energy loss, making them incredibly efficient. One of the most exciting applications of superconductivity is in magnetic levitation, where superconductors can repel magnets, allowing for frictionless movement. This principle is utilized in maglev trains, which glide above tracks, offering high-speed travel with minimal energy consumption. Additionally, superconductors play a crucial role in MRI machines, where they create strong magnetic fields necessary for detailed imaging of the human body. Ongoing research in high-temperature superconductors aims to discover materials that can achieve superconductivity at more accessible temperatures, potentially revolutionizing energy transmission and storage. As scientists continue to explore this fascinating field, the implications of superconductivity could lead to groundbreaking advancements in technology and energy efficiency, transforming how we live and work. Electrical circuits are fundamental to technology, serving as the backbone that powers and connects various electronic devices. At their core, circuits consist of essential components such as resistors, capacitors, and inductors. Resistors limit the flow of electric current, capacitors store and release energy, and inductors store energy in a magnetic field, each playing a crucial role in circuit functionality. Circuits can be configured in series or parallel arrangements. In a series circuit, components are connected end-to-end, meaning the current flows through each component sequentially. This setup is often used in simple applications like string lights. In contrast, parallel circuits allow multiple paths for current to flow, making them ideal for complex devices like home wiring systems, where each appliance operates independently. To design and analyze these circuits, engineers often use circuit design software tools like LT-SPICE and Multisim. These tools enable users to simulate circuit behavior, optimize designs, and troubleshoot issues, ensuring that electronic devices function efficiently and reliably. Atoms are the building blocks of matter, and their structure plays a crucial role in the development of materials and devices. Each atom consists of a nucleus surrounded by electrons, and the arrangement of these electrons determines how well a material can conduct electricity. Conductivity is largely influenced by the number of free electrons available for movement. Materials with more free electrons, like metals, are excellent conductors, while insulators have tightly bound electrons. In the realm of semiconductors, the atomic structure is particularly significant. Semiconductors, such as silicon, have a unique ability to conduct electricity under certain conditions. This property is enhanced through a process called doping, where small amounts of impurities are added to the semiconductor material. Doping introduces additional free electrons or creates holes that allow for better control of electrical conductivity. This manipulation at the atomic level is essential for creating the microchips and electronic devices that power our modern world, highlighting the profound impact of atomic science on technology. Advancements in microscopic technologies have revolutionized engineering and material science, enabling researchers to explore the intricate details of materials at the nanoscale. Microscopy plays a vital role in understanding the properties and behaviors of materials, allowing scientists to visualize structures that are otherwise invisible to the naked eye. Techniques such as electron microscopy and atomic force microscopy have become essential tools in this field. Electron microscopy uses focused beams of electrons to achieve high-resolution images, revealing the fine details of material structures. Atomic force microscopy, on the other hand, measures the forces between a sharp probe and the surface of a sample, providing topographical maps at the atomic level. These microscopic techniques have significant applications in nanotechnology and microfabrication. For instance, they are used to develop nanoscale materials for electronics, improve drug delivery systems, and create intricate microstructures for sensors and devices. As these technologies continue to advance, they hold the potential to drive innovation across various engineering disciplines, shaping the future of technology. Microchips, often referred to as integrated circuits, are the heart of modern electronics, enabling the functionality of countless devices we rely on daily. The process of microchip fabrication involves intricate design and manufacturing techniques, where millions of tiny components are etched onto a silicon wafer. This complex process includes photolithography, doping, and etching, resulting in chips that can perform a variety of tasks efficiently. Microchips play a crucial role in computers, smartphones, and Internet of Things (IoT) devices, serving as the brains that process information, manage tasks, and facilitate communication. They enable everything from basic calculations to advanced artificial intelligence applications, making them indispensable in today's technology landscape. Advancements in microchip technology, such as Moore's law, predict that the number of transistors on a microchip will double approximately every 2 years, leading to increased performance and reduced costs. This ongoing trend continues to drive innovation, allowing for smaller, faster, and more powerful devices that enhance our everyday lives. Mechanical engineering is a cornerstone of technological development, applying the principles of mechanics to design and create a wide range of systems and devices. These principles, which include concepts like force, motion, and energy transfer, are fundamental in developing everything from simple machines to complex structures. By understanding these mechanics, engineers can optimize designs for efficiency, safety, and functionality. One of the most exciting areas of mechanical engineering is the integration of electronics and mechanical systems in robotics. This fusion allows for the creation of intelligent machines capable of performing tasks autonomously or assisting humans in various applications, from manufacturing to healthcare. Additionally, the importance of computer-aided design, CAD software, in mechanical design cannot be overstated. CAD tools enable engineers to create precise 3D models, simulate performance, and streamline the design process, significantly reducing development time and costs. As mechanical engineering continues to evolve, it remains a vital force driving innovation across multiple industries, shaping the future of technology. In this video, we explored the fascinating interconnectedness of semiconductors, electromagnetism, superconductivity, and engineering. Each of these fields plays a crucial role in shaping the technologies that define our modern world. Semiconductors are essential for creating microchips, while electromagnetism governs the behavior of electrical devices. Superconductivity offers exciting possibilities for energy efficiency, and mechanical engineering provides the foundation for innovative designs and applications. As we look to the future, the importance of these disciplines cannot be overstated. They are at the forefront of advancements that will drive our technological landscape. We encourage you to engage with this content by subscribing to our channel, liking this video, and sharing it with others who might be interested. Don't forget to explore our related videos for more insights into these captivating topics. Your support helps us continue to bring you valuable information and discussions about the technologies that impact our lives every day. Thank you for watching.